If two boys have a tug of war using a rope, and in this process the rope rubs against a post such that it is deflected 3 degrees on each side of the post, and if boy A weighs 60 pound whereas boy B weighs 50 pound, to determine if it is possible for one of them to pull the rope towards him, we are provided with the coefficient of static friction between the rope and the post, whereas the coefficient of static friction between the shoes of the boys and the ground is also given to us. Now, to solve this problem, we have to make an assumption that either boy B is able to pull boy A towards them or the other way around. In this case, I'm making an assumption that boy B is able to pull boy A towards him. So to start, let's develop our free body diagram of boy B and figure out all the forces that will be acting on him. So starting with our force in the rope, that will be the tension given as TB, that will be pointed away from the boy. Next, we have the weight of the boy, that is 50 pound. It will act vertically downward. Finally, we will have our frictional force that will be opposing the direction of tension in the rope, going towards the right, represented as FFB, while the normal force is pointing vertically upward. Now, since we are making an assumption that boy B will be able to pull boy A, so the maximum frictional force between the shoes of boy B and the ground will be equals to F is equals to mu N. That's the maximum force before the slipping phenomena starts happening. So that value is equals to zero point 0.5 NB. Now, once we have our free body diagram, let's go ahead and start writing our equilibrium equation, starting with summation of forces acting along the y-axis equals to 0. I get the value of NB equals to 50 pound, whereas the summation of forces acting along the x-axis equals to 0. We have tension acting towards the left, that's why it is given as negative, whereas the frictional force acting towards the right taken as positive. This gives us the value of tension in the rope, TB equals to 25 pounds. Now, once we have the tension in the rope at point B, let's go ahead and figure out the frictional force between the rope and the post. Now, to figure that thing out, we have an expression that is given as T2 is equals to T1 times exponential mu beta. Here, in this case, T2 is representing the tension in the rope that acts in the direction of the intended motion, whereas T1 is the tension in the rope acting in the direction that is opposing the motion. So we have to figure these values out. Next, I have mu, that is the coefficient of static friction between the rope and the post, and it is given to us in the problem as 0.3. Finally, we have beta. This beta is basically the contact angle between the rope and the post. Now, in the problem, we are given that the deflection of 3 degrees is happening on each side of the post. So the value of beta will be the sum of both these 3 degrees. So the total value will be equals to 6 degrees. However, we have to keep that thing in mind that here the value of beta is represented in radians. Now, once we have defined all the variables, let's go ahead and identify the value of T2 first. Since we are assuming that boy B will be able to pull boy A, so the direction of the relative motion is basically the tension in rope at boy B's end, that will be TB, whereas T1 will be the tension in the rope acting towards boy A. So T1 is equals to TA, A. Next, let's go ahead and figure out the value of beta. Since we have beta is the 6 degree that is coming in contact with the rope and the post. However, we need to represent it in radians. So multiplying 6 degrees by pi over 180 degree will give us the value of beta in radians, that is coming as 0.1047. Now, once we have all of these numbers, let's go ahead and plug it in our expression and solve for our value T1. Since T2 is 25 pound and T1 is equals to the tension in the rope acting towards buoy A. So plugging in this information and solving, we are getting the value of TA equals to 24.227 pounds. Now, once we have calculated the value of TA, let's go ahead and figure out the force at buoy A feet to see if he slips and move towards buoy B or not. To do that, we have to develop our free body diagram of buoy A and list down all the forces acting on it. So to start, we have our tension in the rope, and tension will always go away from buoy A. So I'm developing my free body diagram here with TA going away from buoy A. Next, I have the weight of the buoy that will act vertically downward. In this case, we are given the value of weight as 60 pound, that's acting vertically downward direction. Next, we have our frictional force that will oppose the direction of the tension in the rope, represented as F subscript FA here, whereas the normal force will act vertically upward. Next, let's go ahead and apply our equilibrium conditions to figure out these unknown values. So applying the equation of summation of forces acting along the y direction equals to 0, we are getting the value of Na equals to 60 pounds. Next, let's go ahead and apply summation of forces acting along the horizontal x direction equals to 0. In this case, the force between the feet of the buoy A and ground is equals to the tension in the rope, that is coming as 24.227 pounds. Now, once we have this force, next let's go ahead and figure out the force at which the slipping of buoy A will occur. So to do that, we are just going to apply our expression of frictional force for slipping and see if it is greater or less than our 24.227. So to do that, the coefficient of static friction between the buoy A feet and ground is given to us as zero point 0.4, whereas the normal force is 60. Solving, we get our slipping force equals to 24 pounds. Now, since the force that is actually acting between the feet of buoy and ground is greater than the slipping force, it means that the slipping phenomena actually took place and buoy B was able to pull buoy A towards them. So the initial assumption that we have made that it's possible for buoy B to pull buoy A towards him is correct.